collaborative environments and works. This time I have found some new collaborative environments and works that can help us in our research. I have been conducting some research online and I have found that these 5 papers can help us in our research, specifically in the human and AI interaction and collaboration. These papers are efficient learning of safe driving policy via human AI copilot optimization, Watch and Help, an online version of Watch and Help, human AI shared control via policy dissection, and serial bar. Please note that some of the videos don't have sound. So in the previous video we saw how we can get a car to follow a straight line on the road, and some key information about this project is that training is done with a human in the loop, and it is also important to know that this work doesn't have any reward mechanism, which might be helpful since we don't need to model any reward for the learning. So what it does instead is try to maximize the Q value and also tries to minimize the human intervention. If you just look at the left picture in the pictures just below the text, you will see that the environment sends out a state S to both the agent and then the human. And then the agent tries to take action A. The human will judge if the action A is helpful. If not, the human will just correct the action of the agent. And while correcting the action of the agent, an intervention cost is also sent to the agent. So we will try to maximize this cost. In the above work, the human-like agent was implemented as a planning agent, but it can also be a human. And the AI agent action can be implemented either by a policy or by a planning algorithm. In this work, they evaluated three different models. One hierarchical planner, hybrid, which uses both RL methods and planning methods, and also an HRL method, which uses only reinforcement learning. It is also important to note that in this work, they said that the ALICE goals can either be inferred, given, or randomized to Bob. Bob, which is the AI agent, and Alice, which is the human agent. It was found by experiment and results that the AI agent, which uses a Monte Carlo tree search with regression planning, and where true goals were shown to Bob, achieved the best results.
In this work, we aim to build robots that can help humans do different tasks at home. We want these robots to be socially intelligent, which means that they should be able to infer what the humans are trying to do by observing their actions and coordinate with them in achieving these goals effectively. To do this, we hypothesize that robots must conduct probabilistic assistance. Here is an example. When a human walks to the kitchen, the robot will predict all the goals that are consistent with this action, and it will try to help according to all these goals, in this case by walking to the kitchen. The human then grabs two forks, and the robot restricts the set of possible goals, and it helps the human by handing them two plates. Finally, when the human puts the two forks on the dining table, the robot can infer what the goal of the activity is, and it will help by putting the two plates remaining on the dining table. To build robots with such a capacity, we propose a new embodied assistant approach, or NOPA. For more details, please refer to the main paper. To evaluate our method, along with different assistant approaches in a scalable and reproducible manner, we introduce a new embodied assistant challenge, Online Watch and Help. Here we will have a home apartment and a main agent that will be playing the role of a human and will have to do different tasks, for instance set up a table. Meanwhile, a helper agent will have to infer what the task the human is trying to do and help them in performing this task as quickly as possible. We use an open-source multi-agent virtual household platform, Virtual Home Social, to simulate a wide range of real-life household tasks in realistic virtual apartments. We show here a typical example of how our approach successfully conducts online goal inference in this challenge. In the upper right panel, we show the predicates and their counts proposed by the approach as possible goals. For instance, on apple coffee table means putting one apple to the coffee table. We also show the probability of each predicate count pair produced by the approach at each time step. In this example, the main agent wants to set up a table for 3 people. When the agent walks to the dishwasher, our approach eliminates predicates that are inconsistent, in this case objects that are not in the dishwasher. As the agent walks to the kitchen table, the approach eliminates the predicates that have to do with the coffee table, and increases the predicates that are consistent with the actions. And so as the agent takes actions, the predicates will be updated and the helper will be doing the best action to help. Our approach also exhibits interesting emerging behaviors. Notice here how the helper agent hands an object to the main agent so that they complete the task. Or here, where the helper corrects its behavior, in this case, putting the fork back into the cabinet once it sees that the main agent is doing the task alone.
So the above work follows from the Watch and Help paper that we just saw. And this NOPA here model an online inference strategy whereby the AI agent watches and help Alice at the same time. It is also worth noting that in this paper, they improve on the goal inference network and also on the planning algorithm. In this work, they try to find which motor primitives, which is neurons in the neural network, that can initiate some kinematic attributes. Once they find these motor primitives, they would just adjust the value of the motor primitives in order to perform new movements and behaviors. It can be seen in the photograph just below. The neurons, which are colored, are the one that helps initiates movement and therefore can be controlled, and the value of it can be adjusted so that new behaviors can be performed. However, it is not adaptive to human. That is, the human just controls it and doesn't adapt to the human. The last interesting environment which I found this week is the cereal bar environment. It is a turn-based collaborative game, and it consists of two players trying to collect a set of cards and thereby earning points. In this game, there's a leader who has full view of the environment and will instruct the follower using natural language in order to accomplish the task. The follower has a first person view and will try to implement what the leader told it to do. In this work, the player must optimize their movement such that they can accomplish most things in their turns and thereby getting the maximum rewards. There's a nice YouTube playlist online for this work.